So guys, I wanted to do a video on my Nissan Leaf battery bank and my furnace. So I thought today would be a great day to do this because it's about 19 degrees outside and it's supposed to drop to around 3 degrees tonight. So I'm gonna run it probably till around 10 p.m. give or take. Really depends on how long I'm up till. So right now it is 10 after 12 in the afternoon, and what I have here is my Xantrex 1800 pure sine wave inverter, and I have that going into a kilowatt, and an extension cord goes down and it's actually going into my furnace, and my easy generator switch is in the generator position, so it's ready and working in generator mode. So really what this is it's actually tied to the inverter, so it's, for all intents and purposes, it's on generator or battery backup at this point. And I wanted to check a few things out here real quick, and we're going to kind of capture the starting voltage, which should be somewhere around 24.2. Let's just take a peek. Okay, 24.14. Okay, that's our starting voltage as we start this process. And also gonna see if we can see what amp draw this thing's using. Okay, the furnace actually just kicked on, which is kind of cool, so we can get to see the draw. So you can see on the front of the Xantrex inverter we're down to 23.9 using 19 amps, and you see that's 422 watts. I believe we know this thing runs, when the other motor comes on, runs somewhere in the neighborhood of 560 watts. And we'll just wait for that to kick on. So we're kind of bounced back up to 24 because the other motor, the blower motor, did not kick on yet. And what I want to check here is a couple things. We're going to take a look at if we can get this fluke. We're going to see if we can get it around one of the terminals so we can actually see what the battery's drawing, not just what the AC side's drawing here as far as amps are concerned. Okay, you can see how that went up to 843, and then you'll see a drop. So remember, when it initially starts up, that motor draw is kind of high, so we're running at around 553 watts, and according to the Xantrex it's around 25 amps DC. And if you want to look at the amps AC, we can take a peek at that. It's 5.61 measured at the kilowatt, and you can see we're 116.5 on the voltage, which is well within specs. And of course our hertz, which is always right around 59.9 or 60. So what I was hoping to do here real quick was show you the back of the battery bank. So I added a couple wood panels to this so that there could be no problem with touching the bus bar accidentally. And I also have a fuse I installed as well since the last time you saw this. So just going to turn the Fluke DC amp meter on, have it in DC mode, and we're going to see if we can clamp around here. And I would have to spin it around for it to say, you know, the positive, but just take a peek, that's close enough. So it's 26.7, 26.8 DC amps coming out of the battery to the inverter. So you noticed on the front, I think it said 25, so you can see that the inverter itself is using a little bit of amperage and wattage to run itself. And when the furnace shuts off, we will also see if we can get those DC amps in as well. So I don't have my calculator here, but really I would be willing to bet if we took 24.14, which was our battery voltage, and we took that times the amperage, that'll tell us what the real wattage from the battery bank is using. And I wouldn't bet that it's too much higher than 550. I guarantee it's a little bit higher than 550, but it's, you know, we'll do the math here afterwards and see where we're at. But the battery voltage at the measured at the inverter is 23.7. That's what the inverter is measuring. Can almost guarantee it'll probably be a little bit higher. We measure it from the fluke. So actually it's about the same. So 23.66, and I think on the front it said 23.7. Let's just see. I'm not sure if I can get this, but we're going to do it right at the battery. 23.81. So you can see directly at the battery, it's a little bit higher, 23.8, as opposed to running through, you know, the loss you get from actually running through this little bit of wires. I think that's a 4-gauge wire going into the inverter. The fan is running. You can feel the air coming out of the back of the fan, and that's probably a good thing. It's keeping everything cool inside of there. Of course, when the fan's on, it does use a couple watts to run the fan, but it is what it is. So, like I said, my goal is to see how long this will run. Hey guys, so this is with the furnace shut off after that first cycle, and I wanted to see if we can read the amps while it was off. So you can see we're running at about 0.8 amps. So you take 0.8 times 24, and that would tell you how many watts it's using really while sitting idle. And remember, in the furnace there's a it's always drawing a voltage because of a transformer in there that is powering the thermostat. So I'm going to show you the hook it up to the voltage as well. So we're at 24.03 sitting at the voltage. We'll just try it at the battery, see if it's any different. Should be the same. 24.04. And again, this particular multimeter is accurate out to the hundredths, so that's why you're seeing slight difference in voltage from up here as to actually at the battery bank. So I just wanted to catch that while it was sitting idle waiting for the next heating cycle to come back on. So you can kind of see, you know, we're sitting at 23.9 up here. I showed you what it was on the back side, and it says it's drawing 1 amp DC, and you can see it's drawing about 4 watts on the AC side. So you can see the voltage is back up to 120, 0.9 of an amp, 3.9 watts, and if you can look, we're at 0.08 kilowatt hours. Means we're half an hour into it. So come back. Okay guys, here we are at the 1 hour mark. We'll just check that. So actually 1.07, 1 hour 7 minutes. We used 0.18 kilowatts. So what that means is over the course of that past hour we used 180 watts. Resting at 23.9, 1 amp. Remember, we're drawing 4 watts on idle. We'll just take a quick peek over here, see where we are. We're just going to go up to these 2 prongs here and we'll keep a reading. So we're at 23.96 over here. So what we'll do is we will just show you what 23.96 is per cell. So 23.96 divided by 3, that's 798 for the whole module. We'll divide that by 2. So we're sitting at 3.99 right here. So we're somewhere in the neighborhood of 80%, give or take. So again, we used 180 watts according to the kilowatt hour. Now remember, that doesn't account for, that's anything going through the kilowatt meter. It doesn't account how much the inverter is using itself. And if you remember, we're just going to take the fluke meter again, and so we're using, it hovered between 0.5, 6, 7, 8, 9, so I think last time it was 0.07. 0.08, so 0.08. So we'll see what this is actually drawing. So 24. So that's drawing 19.2 watts an hour. So we could take the 100 and, what do we have here? We take the 180 watts and add 20 to it. So we're using around 200 watts an hour with the temperature. And I believe right now it's around 20 degrees, give or take, outside. So it's getting colder as the day goes on. And we'll just keep our eye on it. But the idea is we will stop somewhere when we see the voltage get in this particular range between 3.6 and 3.7. We'll stop. Ideally, I'd like to stop when it goes below 20%, but we'll see what hour we're on when that happens. So guys, here we are after 2 hours, and I just wanted to check on a couple things and show you a couple things. One with the inverter. So this is a Xantrex ProSine 1800, so it's a pure sine wave inverter, 1800 watts. And what this here is a part of the manual where it's talking about the efficiency of this. And if you go over here and look, our average draw is going to be somewhere in the 550, 600 watt range. What we're going to get out of this inverter is about an 88 to 90% efficiency, which I think is very good considering you look at some of the other inverters out there that are 75, 80% efficient. And I also wanted to highlight one thing we looked at earlier. We look at the no load idle mode, which is what it's kind of doing when it's not carrying the load from the furnace. So the spec is less than 22 watts. And if you noticed earlier, when I checked it, we drew 0.8 amp DC times 24 volts. We were getting 19.2 watts. So we're kind of in line with their spec of less than 22. We're sitting at 19.2. And I also wanted to show you, before I get into the measurements here, the furnace is off right now, but I wanted to show you with this power analyzer, it's a Fluke 41B, you can take a look at the sine wave. Let me see if I can get the light on here. I don't know if this is going to make it better or worse, but actually it's on. So there's the sine wave, which is unbelievably good. And I wanted to point that out. That's what this is, a pure sine wave inverter, so it looks just like house electric. So one other thing I wanted to mention here that's very important with inverters and generators, more importantly than inverters, most pure sine wave inverters have a very low total harmonic distortion. If you look, it's less than 3% total harmonic distortion, 1% typical. So we're going to test that as well here in a second. But the point I wanted to make here is with generators, they tend to get a higher total harmonic distortion. I think my own end, one of the own ends I have is 5, I think it's around 5%, give or take, total harmonic distortion. But the nice thing about inverters is it's very, very low. Matter of fact, what I'll do here real quick is try to compare this with the house power distortion, and you're going to get something similar or better on this particular inverter. So I'm going to just switch modes here real quick, and I'm going to go in and take a look at that total harmonic distortion, 0.8% right there, which is unbelievable. Very, very good. So again, it lived up to its spec. The spec called for 1% typical and a less than 3%. So we're sitting at 0.8. Now we're going to also try to monitor this when it comes on, when the furnace comes on, and see if that changes. One could say that it might go up or it might go down, but we'll check it out. So what I wanted to do was, so we're sitting at 0.8 and there's the waveform, and what I'm going to do is just take this out of the inverter, and we're going to just plug it into the household outlet, which is over here. So just bear with me here. Down in my basement. So see if I can get this in the light here. Hard to do with one hand. Okay. So okay, so that's the waveform coming from the wall outlet, and you can see again, almost identical, very clean. And let's take a look at the total harmonic distortion here. Take a look at that. 3%. So I just wanted to prove a point there that the inverter actually has less harmonics than my household electricity. Okay. So I'm going to bring this back over here and hook it back up, and hopefully the furnace comes on here. We're going to have to get our other measurements as well, because we're near we just completed around 2 hours, so I'm trying to think. I think the half hour was, let's see here. Not sure that it's connected in yet. Okay, so got it back in. Sorry about that light coming back in, but we're back. So I think at the hour mark we were what, around 180 watts. So I know at the half hour mark we were sitting at either 80 or 90. So 1 hour would be 180, 2 hours should be what, around 360. So let's just take a look. So there we are, 2 hours and 7 minutes in, and we've done 270 watts. So we're actually doing pretty good. We're less than 360, which is really good. So we're drawing 3.9 watts. We're sitting at 119 volts. 0.9 of an amp right now because it's not really doing anything. Hertz is still always, that's always should be dead on to 60. But the kilowatt hours is 0.27, so it's 270 watts over 2 hours. Okay, the voltage is still sitting very nice, 23.8, and we will come back over here and we're going to take a voltage reading. Doing this with one hand, so bear with me. So we got those connected, and we're sitting at 2391. So we're in really good shape. 2391. We're just going to take it out to the calculator here and just take a look. 23.91 divided by 3 divided by 2. So we're sitting at a 3.98 after 2 hours. Okay guys, now that the furnace is kicked on, you can see that the waveform still looks very, very well. And we're going to take a look at the harmonics. So you can see that the total harmonic distortion did not change at all, which is really good. So again, I guess I should show you that it's running so you can see. So there's the probes. There's the voltage, so we're sitting at 23.3 using 25 amps. So you can see that the waveform looks really good. The total harmonic distortion looks really good. So Again, this is another one of the reasons I went with this particular inverter. It's just a rock solid inverter. We're going to actually take a reading at the battery, see where we sit. So I'm going to just connect right here into the two terminals, and so we're at 23.5 at the battery while it's under load. And let's just do a quick calc on what that is. So 23.5 divided by 3 divided by 2. So you can see we're under load, we're at 3916. Again, if we come over here, 3916. Now that's under load, so we still got a lot of battery left. And just wanted to catch the sine wave and the harmonics while it was under load. So guys, here we are. 3 hours have expired, and we're going to check the voltage at the battery. Actually, we're going to check it up here like we always do. So we're sitting at 23.81, 23.82. So we'll go with 23.81. 23.81 comes up to 23.81 divided by 3 divided by 2. So we're sitting at 3968 per cell, which is really good. Let's just go in here. So we're used 350 watts over 3 hours and 5 minutes, which is really good. So we can see here that it appears that the furnace has not been coming on as much. Now the sun is actually out, and I think that has something to do with it. Almost forgot to do the calculations. So 23.66 divided by 3 divided by 2. We're sitting at 3.94 volts a cell, and again 3.94, and we're sitting somewhere between I guess 65 and 75, somewhere in there. So we're in really good shape. Just as I did the 3.94, furnace came on, so that's great. Here, what we can do is take a look at this under load here, and the blower's about to come on any second. So we'll wait for that to kick on, and then we'll check the voltage under load. So you can see it's sitting at 23.55 amps with the inducer on and the igniters on. And there goes the motor. So once it kicks up and settles in, it should settle somewhere right around 540, give or take. Okay. So we're at 23.2 with 25 amps, and we will check what the voltage is at the battery. Okay, we're at 23.41 at the battery. See, it's slightly different. So 23.41, 23.41 divided by 3 divided by 2. So we're still sitting pretty good even under load. We're at 390 under load, and you can see there we are. So we're in good shape. All right, again, that's the furnace just kicked on. Just show you the 4-minute 9. Okay, guys, it's 5 hours. We started the test at 12 o'clock, 12:15. It's now 5:15, so we've been at this for a solid 5 hours. We're going to check our voltage. The furnace is not on, so this will be good for our test because we want to get this voltage unloaded. And we're sitting at 23.17. Just make sure about that. We'll just check it here. That was at the inverter. Now I'm checking it at the battery. 2318. Okay. 2318. 23.2 on the inverter. 23.0. So you can see we're at the 5-hour mark. 620 watts for 5 hours. Let's just do the math on that. So 620 watts divided by 5 hours. It's around 124 watts an hour. Now let's just go 23.18. Divide that by 3, divide that by 2. And that brings us to 3.86 volts. And if we come over here, 3.85, according to this chart I found on the Nissan Leaf, we're at a 50% battery mark, which is good. We're still in really good shape. Actually, we're a little bit above that, 3.86, 3.85. So we're a little bit above the 50% mark, and we're 5 hours in. So come back in another hour. Okay, guys, hour 6 is 6:15. Right? It's 11 degrees right now. So let's check the voltage. Oh, 2256. So 2256. That's dropped significantly, I believe. 22.56 divided by 3 divided by 2, 3.76. So we are right there in the 30% range. And I believe what we're going to have to do is probably monitor this right now, or the next cycle when it kicks on, to see what the voltage is under load, because I'm curious. We are used up 900 watts in 6 hours, so I think I had that wrong. 900 watts divided by 6. Yeah, I did. Okay, so it gives us 150 watts an hour, and that's about what we've been seeing, give or take, has been what it's been. So the battery, like I said, is in this range here where we're going to want to start watching it a little closer. Once it, we're I think 3.6, somewhere around there, is the knee, and that's where it just drops off, and you don't really get much more out of it. But I'm going to come down when it kicks on again, the furnace kicks on, because I want to see what the voltage is under load at this level of discharge. Okay, we'll come back when the furnace kicks back on. Okay, so I wanted to catch it under load. The voltage is 22.2, and that is kind of what I measured it as well. Let's just check at the battery. 22.34 at the battery. So 22.34 divided by 3 divided by 2 gives us 3.72 under load. So we're still in okay shape. You can see here we're running 558 watts. I guess we're gonna have to keep our eye on this. Now remember, this inverter will shut off. Trying to find one of my other videos. So it's gonna have a warning at 21, which is what we want, and it'll shut off at 20. So at 21, remember, 21 divided by 3 divided by 2 is 3.5. So no matter what, the worst case scenario
is, let's do 20 divided by 2. So we got 20 divided by 3 divided by 2. So at 3.5, we're going to get a warning, a beep, beep, beep. And then at 3.33, it'll shut completely off. So we'll still be in the safe zone as far as taking the battery down to this, 3.6 level. So we'll hear an audible alarm when we get to that point, if I let it go to that point. I don't know how many more hours we're going to have left. I just have a feeling that we're getting close to running out of wattage in this battery bank. Okay, well, we'll tune back in at I think 7:15 is our next check-in. Okay, so here we are, 7th hour, and we're in a low battery, so it's going to shut off most likely. It may complete this cycle fully. Let's see here, 20.09. We got 116, so 1.1. Let's see, we're at 7 hours. It's a very good chance this gets shut off. So 116.6 on the volts. Watts 550. Okay. So it just shut off, which was good to see. So that's what happens. So it was kind of interesting how we saw that. So we just made it, I would say, to the 7th hour. And I'm just going to go ahead and shut this down because it's annoying. So the voltage most likely will bounce back up. 20.45, and let's just see what that is over here. .45 by 3 divided by 2. It's a 3.4. So that would explain the numbers we did before. So we quickly fell off the edge here. We went 3.6. We were last on, I think, at 6:30 or something like that. So there you have it. I'll have to look at the video again, but I thought it said 1.1 kilowatt hours. So you times that by 1,000. That means we used a rough, if that's, my number's right, we used that and we did it in 7 hours. So that was 158 watts an hour and 7 hours. So what we took out of this pack was 1,100 watts out of the pack. And when we started, I believe we were somewhere, I'll have to go back to the first video, but I believe we were somewhere up in this 80 to 90% range. So I don't know. We're going to have to obviously run another test, but you know, if each one of these is supposed to hold 500 watts, you know, 500, 1,000, 2,000, 3,000 watts, totally full. There's no way we got close to that, right? We got 1,100 watts out of it. So, you know, it's very possible that these batteries are worn down from new. Obviously, they're not brand new batteries, and I'm going to have to run some another test and really charge them up to full to see exactly how many amp hours are in each one of these. But it does appear consistent to some of the other people that are getting, you know, 30 some amp hours out of these batteries. So overall, though, considering, you know, what I would use this for, you know, that wasn't bad. You know, I was hoping to expect obviously a little more than 7 hours I was expecting, but again, I didn't have them fully charged either. So ideally, what I'd like to use them for is to run them overnight in a power outage, so I didn't have to run my generator at night.
And ideally, if I went to bed at 10 o'clock at night and got up at 8 in the morning, that would be 10 hours. So that's what I would like to get out of them, would be 10 hours. So what I'll do for my next test is we'll charge these back up, and maybe I'll show a video on charging them back up with a different charger than this one. I actually have a 24 volt smart charger that really wasn't meant for these, but I think we can get it to work. I know it charges at a faster rate. I believe it charges at 24 volts at 30 amps. So just really quickly, 24 times 30 amps. It should charge at 720 watts. So you just saw I took out about 11 to 1200 out of here. So even at 2, that would be 2 hours. I can put 1440 watts back in, and let's just say it would need 3 hours to charge completely up to 100%. So we're gonna go for that next time. We're gonna fully charge this battery up, and we'll run another test and see where we're at. Okay, thank you.